let's do some examples now with RL circuits, and we'll introduce some batteries so that we have a source of potential. So let's say we have a circuit with a 10-volt battery, a 5 ohm resistor, and a 5 millihenry inductor. What is the battery current immediately after the switch is closed? Well, as soon as the switch closes, the inductor opposes the current flow. That means that immediately after you close it, we cannot get a sudden change in current, so our initial current is still 0. It takes some time to build up. Okay, what is the battery current after the switch has been closed for a very long time? So after it's been closed for a really long time, it's not the best diagram, but hopefully it's okay. So there's our resistor, there's our inductor, and there's our battery. Two ways you can look at this. So the first part that's pretty important is that our current is constant because it's been for a very long time. If the current is constant, the change in current is equal to 0, and the potential difference across the inductor, which is minus L di dt, equals 0. So the potential difference across our inductor, and it has no resistance, so there's no potential drop that way. If we write down Kirchhoff's voltage law, we get an increase of 10 volts, plus 10 volts. We get a drop across the resistor, and then we have our potential of the inductor equals 0, and then we can solve for our current. I is 10 volts divided by the resistance, 5 ohms, to get 2 amps. Another way you can think about it is that conceptually, once the current becomes constant and the potential difference across the inductor goes to 0, this acts like a short circuit. And by a short circuit, it means it just acts like a straight piece of wire with no resistance. So if you wish, if you prefer, you can take out your inductor and you can just replace it with a piece of wire. This treatment tends to simplify some problems we'll look at. And then in this case, we would just use V equals IR, I equals V over R equals 2 amps. We get the same result, really for the same reason, just a different way to conceptualize it. Okay, let's do another similar example, but let's just ramp it up a notch. We'll ask the same question. What is the current immediately after the switch is closed and a long time after the switch is closed? So at t equals 0, we close the switch. So that closes at t equals 0. Let's think about what happens. Current is permitted to flow. That's allowable. So current can come out of the battery. Current I can come out of the battery. It hits a junction right here, and it has two choices. It can come down, or it can go to the right. Well, on the right, there's an inductor which resists the change in current. That means that the current in this branch must be 0 because the inductor opposes the flow. So that's because of inductor. So that means that the current that's put out by the battery all goes through the 20 ohm resistor, so the current just flows around the loop this way. So then in this branch right here, this is the only one we'll look at. I is equal to V over R. The only potential is the 10 volts. The only resistance is the 20 ohms. Equals 0.5 amps. So when you have the inductor, no current can flow through it immediately because it resists that change. It takes time for the current to start to flow. So at the very beginning, this acts like an open circuit. Current can't get through immediately. Okay, what is the battery current after the switch has been closed for a very long time? Let's redraw our circuit. Let's think about the idea that after a long time, the potential difference is 0. So there's our battery, 20 ohm resistor, 20 ohm resistor, and the inductor. So for our inductor, delta V of the inductor equals 0 because the current is constant. That means it's like a short circuit. or just like a plain piece of wire with no resistance. So we could redraw our circuit. Got our 10 volt battery, our 20 ohm resistor, and our 20 ohm resistor, and the inductor has been replaced by a piece of wire. This is a simple circuit that we know how to deal with. This is two resistors in parallel. So after a long time, 1 over R equivalent equals 1 over 20 plus 1 over 20 equals 2 over 20. So the R equivalent equals 10 ohms. So after a very long time, the current can flow easily through here because there's no potential drop and the current is constant, and our circuit simplifies to this two resistors in parallel. So then the current that goes around this circuit, we'll say V equals IR, I equals V over R, 10 volts, and this is our equivalent resistance, of course, 10 volts over 10 ohms equals 1 amp. Okay, so we have to think about the behavior of the inductor. At the beginning, that's when it's like an open circuit, and at the end, that's when it's like a short circuit. Okay, let's do another one. The switch in the figure has been open for a long time. It is closed at t equals 0. What is the current through the 20 ohm resistor immediately after the switch is closed? So let's think about what this means. So the switch has been open for a long time. So it means that nothing was happening. So that's what means that it's been open for a long time. When we close the switch, current is permitted to flow out of the battery. So current can come out when it hits the junction. So we'll show that the switch is closed. When it hits the junction, it has two choices. It can come down or it can go across. But our current through the inductor has to be 0 because the inductor opposes the change. That means our inductor acts like an open circuit. So that means that our circuit, as soon as the switch is closed, has our 10 ohm resistor and our 20 ohm resistor, and nothing is happening in this branch, so we wouldn't really need to draw that at all in an equivalent circuit. And then we can say that our potential is V equals I times R equivalent. That would be a series equivalent. R equivalent would be 10 plus 20 equals 30 ohms. So I is the potential, 30 volts, divided by the equivalent resistance, 30 ohms, equal 1 amp. Okay, so that's what happens at the very beginning. What happens after the switch has been closed for a very long time? So what is the current through the 20 ohm resistor after the switch has been closed for a very long time? So that means we've reached steady state. And steady state means constant current. And if we have constant current, there is no potential drop across the inductor. So what can we think about here? We're asked for the current through the 20 ohm resistor. Well, if the potential difference across the inductor is 0, then the potential difference across the 20 ohm resistor also has to be 0, because if we did our loop rule here, the potential across the inductor plus the potential across the resistor equals 0. So therefore, delta V across the 20 ohm resistor equals 0. So the current through the 20 ohm resistor also equals 0. Okay, so you can think about it with Kirchhoff's current law. We can also do that sort of equivalent circuit if you prefer that kind of approach. So we've got constant current here that makes this like a short circuit. It's easy for current to flow through here. So if we redrew that circuit, we would have a 10 ohm resistor, we would have a 20 ohm resistor, and we would have a piece of wire. So what happens in this sort of a system practically is that the current comes out through the battery, and then it has two choices. It could go down through the 20 ohm, or it could go through the piece of wire. Well, what would happen is that since the inductor is a short circuit, all of the current goes through this branch. The current won't flow through a branch with resistance if it can flow through a branch with no resistance. So that means the current through the 20 ohm resistor has to be 0 because it will choose to flow through the wire with no resistance instead of that one. And then if you wanted to find your I, you would do V equals IR, I equals V over R. So it's like this guy is not even here. 30 volts divided by 10 ohms equals 3 amps. The question didn't ask for what is the current output by the battery, but we can find it, so why not figure that out? So after the switch has been closed for a long time, the current flows around the loop this way because it doesn't want to go through a resistor. There's no current through this branch, and the current through this part is going to be 3 amps. Okay, very last part of the question. What is the current through the 20 ohm resistor immediately after the switch has reopened? So it has been closed for a long time, then we open it up again. So let's just get our heads straight about what happens before we reopen it. So this is where we were in part B. Well, I cannot believe I misspelled reopen. It is an odd looking word though. So we've got our battery, we've got our 10 ohm resistor, we've got our 20 ohm resistor, and we've got our inductor, which is acting like a short circuit. Okay, and then what's happening with the currents is that we've got a 3 amp current here, and a 3 amp current here, and 0 amps here. And then we can put in our values if we wish. This is 30 volts, 10 ohms, 20 ohms, and 10 millihenries. So that's what's happening before we reopen it. Well, then what happens when we do reopen? So then we reopen the switch. The inductor still resists the change in current. So once we reopen, L resists the change in current because that's what the inductor does. So the current flowing through the inductor is still going to be 3 amps because it doesn't want to change immediately after we reopen the switch. Okay, so we've got 3 amps flowing through the inductor. I'll label that guy 3 amps. It hits this junction here, and let's ask what happens right here. Well, we've got an open circuit because the switch is open. So we've got an open circuit here. That means no current can flow through this branch. It has to flow through the 20 ohm resistor. So current I is forced through the 20 ohm resistor. So that means the current in the 20 ohm resistor is 3 amps. So if we wish, you could redraw that circuit with the open switch. Since there's an open switch here, we don't even need to include it because there's nothing happening in that part of the circuit. Nothing can flow if the circuit is open. So there's our inductor, there's our resistor, and the current flowing around it is 3 amps. That's what happens immediately after it reopens. If you wanted to ask what happens over time, that's a valid question. What would happen is that the current would decay over time. according to the expression I equals I0 e to the minus t over tau, where tau is equal to L over R. So another question you could ask is, how long does it take for the current to become approximately zero? And that would happen after 5 times the time constant.